Hey, hi. So let's take a quick look at energy units, and because there's different ones, and I want to make sure that you understand them. And we'll also take this opportunity to go ahead and look at energy diagrams for exothermic and endothermic. Okay, share my screen. So when you think about energy units, because this topic we'll be talking about is all about energy. Thermochem, so it's kind of like the energy associated with different processes, whether they are physical or chemical processes. And I wanted to show you the different units that you may see. All right, let me turn this. And let's put some lines on there, guys, shall we? Let's get some colors. Yeah, bright, bright, shine bright like a diamond. We're going to look at energy units. And then energy diagrams in preparation for our next unit on thermochem. Units of energy. Well, we've got several. We're not going to look at all of them. You've got joules, right? J. Kilojoules, you often see. KJ. We've got calories. And we've got calories. You see the difference? One has the capital C and one does not, okay? You've also got kilocalories. All right, so I don't want you to get confused. All of those units are energy units. They are referencing measurements of energy. You need to know that 1 joule, no, let's do this. 1,000, right, joules is equal to 1 kilojoule. You should know that. What you don't necessarily know is that 1 joule is equal to 4.184. Ah, that is wrong. Sorry, I hate it when I make these mistakes. 4.184. 4.184 joules is equal to 1 small calorie. All right. And 1,000 small calories are equal to 1 big calorie. Okay. All right. Another thing is, let's talk real quick about your exothermic, right? Here we know that the products have less energy than the reactants. Oops, let's get the word energy in there. All right, that means that heat is released in this process. Remember that heat is a form of energy, okay? So if you were to look at an energy profile, that just means a graph of the energy change as the reaction progresses in the forward direction, okay? This over here will be our energy, okay? And we will have the reactants here. We always have a bump, and we will have the products here, okay? So what we see is the reactants have this much energy, and the products have this much energy, right? Such that the difference in these energies is equal to the energy of the reaction, right? Delta H is enthalpy, we actually call it enthalpy of reaction. And this is the change in energy for the reaction. Okay, and if my energy profile shows that the products have less than the reactants, we're going to have a negative exothermic energy lost. Okay, I could calculate that by getting the difference between P and R, right? So I would go R minus P here. Okay, now what else could we see here? We could look at the top of the hill. This is something called the activated complex. It's just a very unstable species that are formed in this process of getting from reactants to products. And the difference in energy of where I start and the top of the hill, the activated complex, that will give me, let me change the color, that doesn't look like a very good color. That will give me something that we call the activation energy, right? So in order for this reaction to proceed, it must get over this hill right here, right? So the activation energy is that energy that must be obtained in order to get over that hill. Okay, if I have an endothermic process, then everything is kind of opposite, and the products have more energy than the reactants. Okay, and that means that heat or energy was gained. Okay, so if we look and we have a positive delta H and we have an endothermic process, right? A process that requires us to add energy in order to get it to happen. If we were to look at an energy profile, right? And this was for an endothermic, we would need the reactants, this is your energy over here, to have less energy. There's still a bump than the products. So this would be the energy of the reactants, and this would be the energy of the products. And you see that it's gained energy. So again, the difference between these, right? The difference here is equal to the delta H, and this time it's positive. And that would be equal to the products minus the reactants. Okay. And our activation energy, well, this is still, right? This is our activated complex. And notice our activation energy now, right? It's from where we started. Let me get a different color. All the way to the top of the hill, right? So in order for this reaction to proceed, we've got to gain this much energy. So this is our activation energy. It's how much energy has to get acquired in order to get over the hill and for this reaction to proceed in the forward direction. All right, we assume that these read this way. If you are ever asked about a reverse process, then read backwards, right? And what you see is that if the forward process is endothermic, then the reverse process has me starting with more energy and ending with less energy. So I would have the same delta H, but a change in the sign, right? So the same magnitude, same numerical value, but a change in the sign, okay? And look at what my activation energy for the reverse, right? Look at the activation energy. Let me get a different color there. Right, the E act for the reverse. Well, look how much lower it is, right? It has decreased. E act is for activation energy. Okay? Good job, guys. Good job, guys.